minimum or the maximum. Yeah, that process finding the minimum and maximum actually considered as the optimization process. Yeah, and then you move to the design or control strategy for the process, and then of course you need a technicians or operator to look into the computer GUI, graphic user interface, for example, so that they can monitor the temperature, the pressure, etc. from the computer. Yeah, so you need to train them, and also like you also when you do your simulations in CFD, for example, yeah, you know how to include your boundary conditions, etc. Yeah, but at the same time also perhaps if you know how to explain the simulation result based on the theory, based on equations, it will be more convincing. Yeah, so you can discuss the results as well as compare your result with others. Yeah, so this is basically the engineering process. Yeah, be able to produce the result, discuss the result, and compare your results with others. Yeah. Yeah, so we look into the examples of the blending process to develop our simple mathematical model for this blending process. We've done that. Yeah. So you have all these equations here. Yeah. And many approach, many model we develop, model 1, model 2, model 3. Yeah. Based on the four assumptions that we had last time. Yeah. Conditions 1, conditions 2, combination of conditions 1 and conditions 2. And finally, the fourth one, we change the physical conditions of the process. Change the tank size, for example. Yeah. So that's all together. Some of the examples, how to quantify it, etc. Yeah. And then you also learn about degree of freedom analysis. What it means degree of freedom analysis. Yeah. We have four variables, three parameters, and one equation. That means the degree of freedom is 3. Yeah. And we skip this one, biological reactions, because it's more applicable for chemical engineering. Yeah. So that's what we have discussed last week with regards, not last Tuesday, last lecture on mathematical modeling. Yeah, so we choose chemical processes for our mathematical modeling. In this case, um, a steering liquid inside a tank, yeah, with the additions of heat or variables, temperature variables. Any questions before we move to our proper lecture on further on the mathematical equations? But here we look into Laplace transform. Any question? Did I
Question.
talk? Did I talk too fast or okay for you?
Yeah, it's okay.
Just nice. Yeah. Okay. So you get the point that I try to give to you, and how that relate to the CEO talk last Tuesday. Yeah. Any idea? Okay. Nothing that you want to ask before we move to the next one. You see the mathematical modeling, right? The slide on mathematical modeling.
Yes, you can see it.
Okay. Now I move back to here. So we move to Laplace transform. Yeah. So I will cover this in about 40 minutes or 45 minutes. Yeah. Okay, you can see that Laplace transform, chapter 3 Laplace transform.
Yes, Prof.
You can see the slide.
Yes,
Yes.
I see it.
Yes, Laplace transform. Okay. We look into you have we have discussed on mathematical modeling. Yeah. So from the process, we come up with the mathematical equation of the process. Yeah. Which involve maybe the first law of thermodynamics, for example, or energy equations which involve heat or temperature. Yeah. Or with regards to flow, we look into the continuity equations, for example, so, um, conservations of mass. Yeah. And in other processes, as you remember, yeah, in fluid mechanics, you also learn probably about momentum, things like that. Yeah? Force, yeah, when you're talking about Newton's first law, second law, third law, for example. Yeah. So basically, what we have learned or what you have learned in your first and second year. Yeah, basically to develop the equations for uh, engineering processes, physical engineering processes. Yeah, by understanding the the equations or the fundamental knowledge to develop equations based on this uh, Newton's law, energy equations, uh, s- etc. Yeah. So now we have these equations, and then we want to apply these equations into our control systems. Yeah. As it is, we cannot actually apply these equations directly to our control systems. Yeah. There must be a way to transform these mathematical equations into another mathematical equations that can be recognized by the computer. Yeah, or in other words, the computer language. Yeah. So if you're talking about software like MATLAB or C++, or maybe during my time we use Fortran. Fortran stands for uh, formula translations. Yeah, Fortran, formula translations. Yeah, but now I think seldom engineering students using Fortran, although still very powerful. Yeah, most of engineering students now actually use MATLAB. Yeah, for simple reasons. Actually, MATLAB and Fortran, the way they work, the principle of their working is quite similar. Yeah, they come up with the equations and then convert these equations series or a set of equations into matrix. Yeah, and then from the matrix we have the input and output. Yeah, and that can be recognized by the computer. Yeah, so in fact, if you read a lot with regards to computer language, yeah, um, people like um, uh, the developer of computer language like Mathematica, for example. I think I did mention to you in our class in engineering, economic, and finance last semester or last year. Yeah, they believe that in the next 5 years, probably students, especially engineering students and computer science students, probably do not need to understand the physical process and develop the numerical equations for those processes, but instead learning about the computer language. Yeah, where for any physical process they already have a computer language for that process, and basically they only need to program that computer language into something that the computer can understand and that relate to the control system. Yeah. So when the Petronas Tarigalit CEO talking about artificial intelligence in his talk um, a few days ago, yeah, on Wednesday, uh, he's actually talking about this so-called artificial intelligence. Yeah, where the computer basically having their own language. So you need to learn the computer language. Yeah. Um, and do the programming, and you don't have to learn about the physical processes anymore. Yeah. So there's a possibility in the future. In the future, things like that will happen. Yeah. But um, I think um, it's a good idea if you, as an engineering student, and also having the skill to be a computer scientist. Yeah. If you also know the physical processes, the equations behind the physical processes, probably you can understand what is the computer language is trying to do in the programming. Then by doing that, you are more alert on what is actually happening behind that simulations. Yeah, just like the similar to the scenario just now. Yeah, you not just only key in the boundary conditions, data in and produce data out, for example, and come out with the simulations. Yeah, beautiful simulations, but you can also discuss it and compare your work with others. So if you know the the the, the equations or the theory behind the simulation, probably you will have a good discussions of your results, and you will not make too much error when you compare your work with others worker for similar problems. Yeah? So actually, to do that, actually you need to come up with another understanding in mathematics. That is called the Laplace transform. How to convert the mathematical equations that will be ready for the computer to use. Yeah. And Laplace transform is actually not something that is not new to your study. Yeah. You have learned Laplace transform, I believe, in your Maths 3 or Maths 4, or probably Maths 2. I cannot remember. Yeah. Laplace transform, yeah, which is actually a standard notation in dynamics and control, a shorthand notation. So the computer will not look at the long equations that we have discussed last week. Yeah, they will not look into the long mathematical equations that we have developed for the processes that we have seen last week. Yeah, even probably some of you noticed that last week, for example, when I start to read the equation, you feel lost. Yeah. So now I'm telling you that the computer also feel lost. They want to have their own language to interpret this equation. So they will apply what's called the Laplace transform. So they transform that mathematical equations, yeah, using Laplace transform into another set of equations that can be easily read by the computer. In other words, to make the programming much simpler. Yeah. So it's true then that if you know the computer language well, then you don't have to know the equations. So it's true then. Yeah. You just master the computer language. Yeah. Then you come up with your own computer equations. Then you can come up with a program. Yeah. So um, I just re-emphasize Laplace transform, basically converting the mathematical equations into algebraic operations. So in other words, now we convert the mathematical equations into algebra, yeah, algebraic operations. Again, you have learned this in your Maths 2 and 3. Yeah, and by only looking at the block diagram analysis, you can come up with a program. Yeah, so that's the idea. Yeah, so that is what the computer scientists are doing. Yeah, and normally in engineering activity, those programmers are being well paid compared with the engineers who actually come up with the process. Yeah? I remember when I worked with Pranican, um, modify their burner management systems 5 or 6 years back. Yeah? We engineer working to actually to pipe the landfill gas from the landfill to the incinerator. Yeah? So we can burn the landfill gas which is methane into the um, uh, incinerator, which is basically a burner. Yeah. So by doing that, you reduce the amount of diesel oil that they need to burn inside the incinerator to burn the waste, yeah, chemical waste, industrial waste inside the incinerator. Yeah? Because a landfill gas, which is methane, is also combustible. Yeah? So we work very hard under the sun, but the programmer who do the adjustment to the burner management system. Yeah. In this case, they apply PLC, Programmable Logic Controller, PLC. He did the work for 3 weeks. We paid him 250,000 for 3 weeks, and his only asset is really some tools, measurement tools. Yeah, and other than that, um, his other assets actually his brain. So he sit in the room for 3 weeks, hardly going out from the room. And after 3 weeks, he come out with a new program for the burner management systems. Yeah, and he only analyzed um, the block diagram. Yeah, program analysis, the block diagram for the processes in the plant, yeah, in the incinerator plant. Yeah, I don't think he bothered to look into the mathematical equations, yeah, but actually he looked at mathematical equations in the form of algebraic operations. Yeah, and he paid 250,000 for a 3 weeks job, and we as an engineer, mechanical engineer, doing the piping, doing the digging, and put back the soil on the pipe to be buried. Some of it is actually 7 meters underneath the ground. We only paid 50,000. So a fifth of his pay, and we did the job for 8 months, and he only did his job for 3 weeks. Yeah, so there is the difference between those having the programming power or knowledge, yeah, and who are more ready for artificial intelligence. Yeah? And that's the value of that kind of skill in this case. Yeah? Require not just engineering but also critical thinking skill on the engineering knowledge to apply it in programming. And of course, engineer can also do that actually, yeah? But you need to know some what it means with optimizations, artificial intelligence, and also you need to know about programming. Yeah. So, in other words, whatever the CEO of Petronas Trigali said in his lecture last Wednesday are very true. Yeah. Any questions? Any questions on Laplace transform?
No question.
Okay, good. Everyone clear on what I tried to say or share with you? Okay, if none, then we look into what is actually Laplace transform. Yeah. Remember your mathematics 2 or maybe mathematics 3 when you learn about Laplace transform, you come up with a letter L, which is representing Laplace transformation. So L in the bracket of functions f as a terms of t, yeah, and that normally followed with the integrations, yeah, or differentiation. Yeah. For example, if you have equations Laplace transformations of functions ft equal to the integration from limit 0 to infinity function ft times uh, e power st, yeah, integrated with respect to time dt. Yeah. Then we have these equations as given there. So we have LA equal to that form, yeah. And interestingly, you can see there, yeah, LA of this equation, yeah, ending up just A over S, this one here. So A over S. So A is a value, maybe 1, 2, 3, 4, 5. And S is that symbol for Laplace transform. Yeah. A over S, A over S squared, A over S cubed, or A over S minus 1, etc. Let's go to the next one. 1 over A become 1, for example, but S is maintained, so it becomes S plus B, for example. Yeah. Etc. Yeah. So we also define that normally f0 equal to 0. Yeah, that's the error. Yeah. So this one example of Laplace transform in the form of integration, and as you have learned in your math 2 or 3, I can remember exactly. And then we also have other Laplace transform in the form of differentiations. Yeah. So this is the second order differential equation, d2f over dt squared. So Laplace transformation of d2f over dt squared equal to L of d phi over dt, where phi is ft. Yeah? And for this type of differentiation, the Laplace transformation, yeah, we're given as s is there, s square fs minus s f naught minus f dash naught. Yeah? And we also have Laplace transform for cos and sine. Yeah, for example, we have a Laplace transform for cos omega t, for example, in the form of f over s square plus w omega square given here. And for sine L sine omega t will be given as omega or w, w is omega or lambda is right, over s square plus w square. Yeah, and many others. And yeah, so basically in Laplace transformations, yeah, which is summarized in table 3.1, which is this one here. Yeah, so we have Laplace transform for functions ft for input impulse, fx is 1, step, unit step, 1 over s, rem with 1 over s squared for functions t for n minus t. The Laplace transform will be n minus 1 over sn. For e minus dt, it's epsilon e minus et 1 over s plus b, yeah, and 1 over 2 e minus t t over tau will be this type. Yeah. So you have one, two different Laplace transform for various time domain functions. Yeah, for various time domain functions, we have for t n minus 1, so 1, 2, 3, 4, 5, 9 here, and also here another 10 here, yeah, 10 up to 19. So many for sine, for cos, for sine omega t plus theta, for example, yeah, and another 7 here up to 26, etc. Yeah. So basically, computer language basically know what is a FP that you have, and then we come out with the FS, which is will be recognized by the computer system, the computer program. Yeah? So if you look at the here, yeah, the step here, yeah, or the general procedure for solving an ordinary differential equations using Laplace transform. So step one, we have the ordinary differential equations with the initial conditions. We apply the Laplace transform. That's the table 3.1 just now. And in step 2, we apply for the output equal to ns over ds. Yeah. And then step 3, factor ds, we can perform the partial fraction expansions. And then finally, we have the inverse Laplace transform given in table 3.1 just now. So from Laplace transform, we go back again to inverse. Yeah. We have the solution for yt. Yeah. So, here. So if you look into one example, yeah, example 3.1, solving the ordinary differential equations, ODE for equation, this one here, 5 times dy dt plus 4y equal to 2, where the boundary condition is not equal to 1. Then if you take Laplace transformation, so L is stand for Laplace, take Laplace of both sides of equation 3.26 here, then you have 5 as a constant, take it out, dy dt become sys minus 1, yeah, so the dy dt is sys minus 1, plus 4 as a constant, take it out, y become ys equal to 2 is a constant, and Laplace transform in Laplace become 1 over s equal to 2 over s instead. So rearrange, we will obtain ys in the form of 5s plus 2 over s times 5s plus 4. Yeah, that is the Laplace transform. And from this one here, based on table 3.1 just now, we take the inverse Laplace L minus 1, so inverse Laplace, we have yt, the small yt equal to the L minus 1 Laplace transform of fs plus 2 over s 5s plus 4, which from table 3.1, you can check, it become yt given by 0.5 plus 0.5t to the power minus 0.8t. Yeah? So this is actually the equation that the computer will recognize. Totally different from the physical equation that you obtained earlier. Yeah? So that we use Laplace transforms to do this. Yeah. So now perhaps relate back. You can relate back what you have learned in mathematics 2 and 3 during your first and second year. I believe in your second year, then you can make some sense on why you need to learn maths at this level. Yeah. And just now I mentioned that those programmer they earn the bulk of the payment in any project. To be honest, I think they deserve it because not many people can master this. All right, you agree? So if you can master this, of course you can demand more, and this because this is basically require higher order thinking skill altogether. Agree? So you cannot blame them. So personally, when I'm being paid 50,000 for 8 months work, and those working in the control room in the aircon being paid 250,000 for 3 weeks, initially I complained, but when I think about it, I should not complain, but probably I just need to admire them. Yeah, because they really uh, uh, how do you call it, crush your brain to really understand these equations. Yeah, so you cannot rely on them. But in the future, as the CEO of Petrastically say, when artificial intelligence being applied more widely, yeah, and then graduates need to learn at least one or two computer language, I think become a norm. And probably the pay between a programmer and an engineer probably can be the difference. The difference between the pay probably getting less because now the programmer cannot say that only them can do that, but also engineer also can do the job as well. We can demand a bit of the pay as well. So another examples. This is in third order differential equation, d cube y over dt cube, for example, plus 6 d square y over dt square, plus 11 dy dt plus 6y equals 4. Yeah. For this one here, if you apply the Laplace transform, LT, and then you use the partial fraction decomposition and take the inverse Laplace transform. Yeah. And this is for response unit step at t bigger than 0. Yeah. So this equation here, the Laplace transform, yeah, noting the 0 initial condition, you will have it in the form of this one here. Yeah. d cube y over dt cube become s cube ys. Yeah. So 6 d cube y over dt square becomes 6 s square ys on 11 dy dt simply become 11s times ys. And so ys is still always there. Ys is stand for the output. Later on, you look into output and you learn about transfer function. But we do that Tuesday next week, not today. But today we just focus on Laplace. Next week we look into transfer functions. We look in more detail what it means with this ys. Plus 6 pi s equal to 4 the constant the Laplace transform becomes 4 over s here, 4 over s. Okay. You can see the Laplace transformation there. So this is the simplest form actually regards to dy dx differentiation, as you can see, as we have probably noted in table 3.1 just now. Yeah. Uh, um, for integrations and differentiation, the Laplace transform is quite straightforward. And also for cos, sine, etc. Yeah, cosine and sine, the trigonometry is quite straightforward. But when we come to ln and log, yeah, they become a bit more complex. Yeah. So as you can see, ys actually the output, the symbol for the output ys. So we rearrange with respect to ys. So ys in the form of s. Yeah. So yeah, that equation is on here just now. If we rearrange ys now become 4 over s cubed plus 6s squared plus 11s plus 6 times s. Yeah. So by doing that, we have learned about mathematics. I think you understand what this means. So s plus 1, s plus 2, s plus 3 come from this equation here. Yeah. So s, in this case, if we rearrange, we can obtain s times s cubed plus 6s squared plus 11s plus 6 equal to this form here. S times s plus 1, s plus 2 plus s 3. I cannot remember where you learned this one here. Math. But I think you remember, yeah, we did this in maths. So basically, this one here, s cubed plus 6s squared plus 11s plus 6 is actually the multiplication of s plus 1, s plus 2, and s plus 3. We factorize it. Yeah. And step B, use partial fraction decomposition. We have this form here. 4 over s times s plus 1, s plus 2, s plus 3 equal to alpha 1 over s plus alpha 2 over s plus 1, alpha 3 over s plus 2, alpha 4 over s plus 2. And then we can multiply by s, yeah, and setting s equal to 0. And here s equal to 0, the limit. Then you attempt 4 over 1 times 2 times 3 equal to alpha 1 equal to 2 over 3. Yeah. So for alpha 2 multiplied by s plus 1 and set s equal to minus 1, which is the same procedure for alpha 3 and alpha 4. You obtain alpha 2 to the minus 2, alpha 3 to the 2, and alpha 4 to the minus over 3. And from here, you can take the inverse of Laplace transform, table 3.1 now. We're ending up with ys equal to 2 over s minus 2 over s plus 1 plus 2 over s plus 2 minus 2 over 3 over s plus 3. Yeah. The inverse is y2, the small y now, y2 equal to y is the function of time t, so the 2 over 3 minus s plus 1 is 3 minus t, yeah, so become 2 into t, s plus 2 becomes 2 of minus 2t, so become 2 to 2, and s plus 3 to minus 3t taking times as towards infinity, so yt becomes 2 over 3, and for t equal to 0, you have y equal to 0. And then you can use this method on any order of ordinary differential equations, limited only by factoring of denominator, polynomial, or the characteristic equation. You must use modified procedure for repeated roots and imaginary roots. Yeah? So you learn about real and imaginary roots in maths as well. Yeah? So in this case, in short, we can say that the Laplace transforms can be used to process control for one, solutions of differential equations, and that differential equations need to be a linear differential equations. Two, analysis of linear control systems, there is a frequency response. So the question that if it's non-linear, how to analyze? Actually, you also learn in maths. For non-linear, you can linearize it. So that's why we non-linear, we linearize it first, then you can solve it using Laplace transform. And third, predictions of transients response for different inputs. So for example, the equation is not 2 over 3s squared plus 4s plus 1. When you apply the factoring the denominator polynomial, you obtain 3s squared plus 4s plus 1 is equal to 3s plus 1 times s plus 1. Yeah. And that equals to 3 times s plus 1 over 3 s plus 1. So you transform to e 4 minus 3 over 3. So 1 over 3 becomes minus 1 over 3. Okay. 1 becomes minus 1, so e minus 3 is very good. And in this case, since they are all real, it's no oscillation. Yeah. But in this case, another equation of 2s 2 plus s over s2 plus s plus 1 is not here. Here we have the imaginary root given symbol j. Yeah. So here we can transform, for example, e to the power of minus 0.3 times sine square root 3 over 2 times t. Yeah. The oscillation. Yeah. If you look at table 3.1 by line 17, yeah, just show to you here. Table 3.1 here, Laplace transform for various time domain functions. So row 17 here, which is this one here. So b and omega real, you have the Laplace transform fs is given by this one here. Yeah. Then look at here, we have this solution for that. Yeah. Okay, from e minus dt sine omega t, the Laplace become omega over s plus t square plus omega square. So that becomes 2 over h square plus s plus 1 equal to 2 over s plus 0.5 square plus square root 3 over 2 square. And if you simplify further, you obtain this one here. Yeah. e minus bt cos omega t, Laplace becomes s over s plus t square plus omega square. There's the thing for rectangular path input. The path element. So if h is 1, the path input we have this equation here based on the Hopital's theorem. Hopital's theorem. I think I have Hopital's theorem if you learn math. 3 also covered this theorem. Yeah? Which I cannot really remember, but I think you can find it in Maths 3. Yeah. So difference of two-step inputs st minus st minus 1, where st1 is the step starting at t equal to h equal to 1, and by Laplace transform that fs equal to 1 over s minus 2 for t minus s over s, which can be generalized to steps of different magnitudes, step of different magnitudes of a1 and a2. Yeah? And one other useful feature of the Laplace transform is that one can analyze the denominator of the transform to determine its dynamic behavior. Example, for ys equal to 1 over s squared plus 3s plus 2, then the denominator can be factored into s plus 2 times s plus 1 by using the partial fraction technique. Ys equal to alpha 1 over s plus 2 plus alpha 2 over s plus 1. And the step response of the process will have exponential terms of e minus 2t and e minus t. Yeah, this one here. S plus 2 is become e minus 2t. Yeah, s plus 1 becomes e minus t, which indicates yt approaches 0. And we also know that y is equal to 1 over s squared plus minus s minus 2, which is s squared minus s minus 2 is equal to s plus 1 times s minus 2. Then we know that the system is unstable and has a transient response involving e to the power of 2t and e to minus t. When e to t is unbounded by large time, then we shall use the concept later in the analysis of feedback system stability. So what one of it? And there are many other applications as well. For example, the final value theorem for y to infinity, for example. Yeah. Um, get the step response of ys is 1 over 2 s plus 1 times a over s, for example. That becomes taking out the s outside, and get it. You have s y s equal to a over 2s plus 1. So for s equal to 0, this term becomes a. Yeah, so now you make something why you need to learn maths 2, maths 3, maths 4. And this is applicable to the ex-diploma students. Remember, when you after your diploma, you generally ask for your degree. Maths 1 actually covering your maths 1, maths 2, maths 3 in your diploma. So maths 2, maths 3, maths 4 is typically something new. Agree? Yeah? But if you're doing your STPM, at maths, for example, or at maths, probably it's okay for you to learn maths uh, 1, I mean, basically in your hand. So maths 2, maths 3, maths 4, you have a strong foundation. And in control systems, it's easier to do a lot of maths 2, maths 3. Yeah? And maths 4 later on, when you're talking about all the historical diagrams and statistics like that. Yeah? And then also the initial value theorem. Yeah. So when t equals 0 yt, we have the limit of s towards infinity of s ys. Yeah. So for the equations, ys, the Laplace equal to 4s plus 2 over s times s plus 1 s2 plus s3, as we seen earlier. So if y 0 is to 0, so by initial value theorem, and then for y equal to infinity equal to 1 over 3 by the final value theorem. So, well, that's all about Laplace transform. So the next actually we are going to look into this y, yeah, for not just one equation, but ys of many equations, and you combine together and you come up with what's called the transfer function in the next chapter. Yeah, so I stop here. I don't want to jump straight to the next lecture. Otherwise, you will crash. Yeah. Any questions? So next week on Tuesday, we look into for Laplace transform. From there, we look into the transfer function. Yeah. And then after that, then um, I will also finalize your um, assignment that will replace your final exam. Normally in the previous years, the final exam questions is more like a concept based on concept. Yeah. But now you have more time to do the final exam because you're doing a assignment. Probably you can do a bit more calculation on this concept. So I have in mind actually to include what we have learned in um, theoretical model, development of empirical model for a process. Yeah, as you understand the control terminology. Yeah, and then finally ending up with the transfer functions. Yeah? After you develop the empirical model, apply the Laplace transform, and finally come up with a transfer function for that process. Yeah. So by doing that, you also need not just need to develop the mathematical equation or numerical model and apply Laplace transform and finally obtain the transfer function. Also, you need to come up with the block diagram of the process where you want to obtain the transfer functions. Yeah. So next week we learn about transfer functions. We discuss transfer functions and what is actually transfer function and how that how Laplace transform being used to obtain the transfer function. Yeah, and I will conclude in week 13 the general instrumentation optimizations of the control systems. Yeah. Any questions? You can speak out. Use your mic to ask me questions, or you cannot use mic. You can post your questions also using chat. Open the chat. To questions. Any questions?
No question.
No question? So you can see that you can back to mathematics when you learn about control